Test chest. Well, let's open the box and see what's inside. Manual. Well, you won't be needing that, you're an engineer. Flow diagram, generation, audio, video, signal monitoring, audio and video. The test chest itself, touchscreen controlled, power supply and battery charger, and in the lid an audio interface that snaps onto the end of the test chest itself, toggling for security. But more of this later. So here you are, faced with your ultimate nightmare. Bunch of cables, barely labelled, analog, AES, composite video, SDI, 3G, HD, who knows? Test chest will tell you though. Now, I'm going to start this demonstration of the witch wire mode in action by turning the unit off. And for the purposes of the demonstrations, I'll be using a coffee stirrer to avoid obliterating the screen with my finger. Now, applying an input, in this case composite video, the unit wakes up and declares its input as 525 CVBS at the top here. If I remove the input, the unit will automatically power down and await its next stimulus. In this case it will be an SDI source, 525 SDI, this case with embedded audio. Powers down again, 720p 50. Now in this case I'm going to leave the unit turned on and tell it it's a monitor. Now in these conditions it will be awaiting an input without powering down, so it's even faster because it doesn't need to go through the power up algorithm. 1080, virtually instantaneous, 1080i 50. I'll just do that again. Virtually instantaneous. 720p, virtually instantaneous. And a 3G source. Again, virtually instantaneous. Back even to composite video, and the unit powers up without any hesitation whatsoever. So I think that's pretty impressive. I'm going to run through the basic menus now of the test chest. I'll turn the volume down, it's a touchscreen volume control. We had a 525 SDI source applied, which we'll be looking at in a moment or two. Waveform monitor mode, conventional waveform time bases. Touchscreen control, so we can move the trace around the screen. Magnification, we can move the trace across. Embedded audio. Parade, YRGB, RGB and component. To field, magnification, and we can pan across the screen and the declared line count appears at the top here. We have the ability to lock the waveform monitor mode to an external reference for when we're doing horizontal timings. Vector scope, magnification mode for white balance checks with a camera. We have two inputs to the witch wire, to the test chest rather, a witch wire mode which we normally use and a high impedance scope mode which is available for use with a probe where appropriate. Monitor mode we've already looked at, audio monitoring. We can select which group we look at by tapping the embedded group. In this case we have got a numeric display at the top and a histogram, dynamic histogram of the audio level. The numeric value is particularly useful for tone measurements, whereas the histogram is obviously valued with program measurements. We can alter the scaling, ppm, BBC style ppm, VU with VU characteristics, Nordic, and then back to digital. In the case of the digital, the maximum scale 0 dBF down to -30 here, and we can add gain blocks of 30 and 60 dB, which will enable us to measure rather lower signals from, for example, digital microphones. We have AES inputs, which we'll look at in a moment, and an analog input, which we'll examine again. Generate audio, very straightforward. Binary selection of tone, frequency, up, down, any level you want in dB steps. Ability to enable or disable individual channels, but we have an ident mode which is enabled at this moment, and you'll notice that the channel 1, 2, 3 and 4 are being successively identified, which enables you down the line to make absolutely certain what you've got is correct. Test signal source, AES we can apply and add to the embedded audio, and an embedded source we can strip the audio off and add it to the output. For line idents and so on, we've got the ability to enable and disable the AES outputs and the analog outputs. AES audio. Now I've got a balanced feed at 110 ohms coming in on the XLR. Included in the audio pod, which we've now coupled to the test chest, is a transformer 110 ohm to 75 ohm, and we've simply taken the 75 ohm output impedance of the transformer and looped it across to the AES input. So we converted the balanced feed to unbalanced at 75 ohms. Similarly, the output of the unit when it's generating is 110 ohms balanced, and if we require an unbalanced output we simply couple it across through the transformer and take it off, so the unit will handle 110 and 75 ohm sources and destinations without difficulty, correctly matching in both cases. Now, AES input. I'll select the AES input. We're now hearing the audio, we're seeing it on the meter, and if I apply an external reference, which I'll apply to the witch wire input, it'll declare it to be locked, or not locked if that is the case. Uniquely, Test Chest handles analog audio correctly. XLR3s are employed with no headphone sockets at all, you'll be pleased to hear. I'll select the source on the analog input. Immediately histogram, stereo phase with the numeric display at the top. Only 2 channels of course are displayed with a stereo on analog. Inside this case is 50 meters of coiled 75 ohm miniature coaxial cable, at the end of which are these switches. Normally the signal is terminated in 75 ohms 0.1%. However, we can add an additional 5 meters of 50 ohm coaxial cable which we switch in and you'll see that effect, or we can add a 100 millimeter long stub, that's about 4 inches of unterminated coaxial cable, and you'll see that effect, or we can vary the termination resistance from a precision 75 ohms to anywhere between 70 and 80 ohms. I'm going to demonstrate the test chest's cable test mode, which uses TDR techniques. I'll power the unit up, select the TDR mode, choice of 3 pulse widths, 32, 64, and in this case we'll select the 32 nanosecond pulse, which is launched into the unknown cable. We're using our demonstrator as the load, and at the end of that 50 meters of 75 ohm coaxial cable, I'm going to add that additional 5 meters of 50 ohm coaxial cable, and the iterative impedance mismatch is painfully obvious. If I add just 100mm of unterminated cable at the end. That too is quite obvious. Or I can add a variable resistor which will swing the terminating resistance from 70 ohms up to about 80, and there's little doubt that the correct value is around there. Now surprisingly, this isn't on the demonstrator 50%. It represents about 73 ohms, 72, 73 ohms, which is the iterative impedance of the coaxial cable inside the unit. So the test chest is actually capable of determining the impedance of the cable used. Right, now I'm going to demonstrate just how fast test chest is to you. I've got two units working in series here. One on the right is set up as a generator, output here. One on the left is set up as a receiver with its input down here. I'm going to set the receiver into its TV monitor mode, and I'm going to set the generator into the set standards mode. SDI 525 rather, SDI 625 SDI 1080 60 50 720 and 3G. Now, as I've explained, this unit here, touchscreen, interpreting what it's seeing, setting itself up to generate the required standard, which it outputs, this unit interpreting what it sees and showing us on the screen, all virtually instantaneous. So I think that's pretty impressive. And equally impressive is Test Chest's flashlight. Aha! There's that manual we lost earlier.